In 2017, a nearly 40-year-old spacecraft, already farther from Earth than any human-made object had ever traveled, started picking up something that, according to every model built to describe the space it was flying through, shouldn't have been there at all. Not a burst, not a one-time spike easily dismissed as noise, a persistent, ongoing signal present in the data year after year, stretching across a region of space larger than anything any single instrument had ever measured from the inside before. This is the real story of what Voyager 1 actually detected once it crossed into interstellar space, and why the scientists studying that signal have spent the better part of a decade trying to fully understand what it's telling us about the space between the stars. To understand why this discovery happened at all, you need to understand exactly where Voyager 1 was and how it got there. Launched on September 5th, 1977, Voyager 1 was originally built for a mission expected to last somewhere around 5 years, a close study of Jupiter and Saturn before quietly concluding its work. It didn't quietly conclude anything. It kept going, kept transmitting, kept accelerating outward, and on August 25th, 2012, it did something no human-made object had ever done before. It crossed the Heliopause, the outer boundary where the constant outward pressure of our sun's solar wind finally gives out entirely, and passed into true interstellar space, the actual material that fills the vast gaps between star systems across the galaxy. The crossing alone was an extraordinary achievement, but it also created something scientifically unprecedented. A functioning, if aging, scientific instrument sitting directly inside interstellar space for the very first time in human history, capable of measuring that environment directly, rather than inferring its properties indirectly from telescopes and models built entirely from the comfortable distance of Earth. And starting in 2017, one specific instrument on board began recording something genuinely unexpected. The instrument responsible is called the Plasma Wave Subsystem, and its job is to detect oscillations, essentially specific kinds of vibrations, occurring within the surrounding plasma, the electrically charged particles that make up the thin, diffuse material filling interstellar space. What Voyager 1's plasma wave instrument began picking up was a persistent narrowband emission, a kind of faint, continuous hum embedded in the surrounding interstellar plasma, one that, according to the models scientists had built before Voyager 1 ever got there, simply wasn't supposed to exist in this particular way. Here's why that mattered so much to the researchers studying the data. Before Voyager 1 actually crossed into interstellar space, the leading scientific expectation, built up over decades of theoretical modeling, was that the plasma filling the space between stars should be relatively calm and largely uniform. A thin, cold, mostly featureless environment where charged particles drift slowly, and comparatively little happens on any particularly dramatic scale. Essentially, a quiet, mostly empty waiting room sitting between one star system and the next. Voyager 1's own instruments told a very different story. Starting in 2017 and persisting for years afterward, this specific plasma oscillation kept showing up in the data, not as an isolated event, but as a sustained ongoing signal detected across a genuinely enormous stretch of Voyager 1's continuing journey outward, stretching across more than 900 million miles of interstellar space. For context, that's roughly 10 times the entire distance between the Earth and the Sun, meaning this wasn't some small, localized anomaly. It was a broad, sustained feature of the interstellar environment itself, present across an enormous span of the specific region Voyager 1 happened to be passing through. Researchers analyzing this data published their findings in the peer-reviewed journal Nature Astronomy, and their conclusions were direct. Interstellar space, at least in this particular region, is not the quiet, largely uniform environment that pre-Voyager models had generally predicted. It's genuinely turbulent, containing real physical structure across an enormous range of scales, from variations measurable in mere meters all the way up to structures spanning millions of miles, an entire hidden landscape of motion and complexity that had simply never been directly measured by any instrument positioned inside that environment before Voyager 1 happened to fly through it. It's worth pausing here to genuinely appreciate exactly why this particular measurement was even possible in the first place, because it involves one of the more remarkable pieces of engineering resilience in the entire history of the Voyager mission. Voyager 1's original plasma science instrument, a separate device specifically designed to directly measure the speed, density, and temperature of surrounding charged particles, had actually been damaged decades earlier during the spacecraft's close flyby of Saturn back in 1980 and never fully recovered afterward. That left Voyager 1 was one without its most direct tool for measuring plasma density once it eventually reached interstellar space. The plasma wave instrument, the one actually responsible for this 2017 discovery, became the mission's primary remaining tool for indirectly inferring plasma density instead, by carefully analyzing the specific frequency at which these oscillations occurred, since that frequency itself carries embedded information about how dense the surrounding plasma actually is at any given moment. This turned into something genuinely valuable precisely because it was ongoing and continuous, rather than a single isolated measurement. Before this persistent signal was identified, scientists studying interstellar plasma density near our solar system had mostly relied on isolated, occasional snapshots, individual measurements triggered by specific, relatively rare events, such as shock waves produced by major eruptions on the sun's surface, eventually traveling all the way out to the heliopause and beyond, sending detectable ripples into the surrounding interstellar medium. Those kinds of measurements were valuable, but scattered and infrequent, roughly comparable to trying to understand an entire continent's weather patterns by checking a single thermometer in one city only once a year. What this persistent plasma oscillation actually provided instead was something far closer to a continuous, ongoing feed, a running, real-time portrait of interstellar plasma density as Voyager 1 continued moving through it, year after year, rather than relying entirely on rare, scattered snapshots. There's a genuine, still partly unresolved scientific question sitting at the center of this entire discovery, one that researchers working on the Voyager data have been actively trying to answer since the signal was first identified. The persistent emission has two distinct possible physical explanations, and distinguishing definitively between them has proven genuinely difficult. The first possibility is that the signal represents thermally excited plasma oscillations, essentially the natural, ordinary vibration of plasma particles interacting with their immediate surroundings. If that explanation holds up, it would still be a genuinely significant discovery, but one that fits comfortably within existing physical frameworks, without requiring any fundamental rebuilding of how scientists understand this environment. The second possibility is that what Voyager 1 is actually detecting is something called quasi-thermal noise, a distinct physical mechanism that, while still carrying useful information about plasma density and temperature, would point toward a subtly different and considerably more consequential underlying physical process, one that would require meaningfully revising existing models of how the interstellar medium actually behaves. Fully resolving that specific question would require either considerably more data gathered directly from Voyager 1 itself, or an entirely new mission purpose-built to study interstellar space with instruments specifically designed to make exactly this kind of precise measurement. Neither option is currently straightforward. Voyager 1 continues producing less usable data with each passing year, as its dwindling electrical power forces mission engineers to permanently shut down additional scientific instruments simply to keep the spacecraft's most essential systems functioning at all, and no replacement mission specifically designed to study interstellar space currently exists or is currently funded. Even if such a mission were approved and launched today, reaching the same boundary Voyager 1 crossed back in 2012 would likely take at least another 25 years, given the enormous distances and travel times involved in reaching the true edge of our solar system. That timeline matters enormously, because Voyager 1's own operational life is now measured in a shrinking number of remaining years, not decades. The spacecraft runs entirely on radioisotope thermoelectric generators, converting the steady, irreversible decay of onboard plutonium into usable electricity, losing roughly 4 watts of available power with each passing year. Of the 10 scientific instruments Voyager 1 originally carried at launch, the majority have already been permanently shut down, each decision made carefully, years in advance, by a mission team forced to weigh the ongoing scientific value of every remaining instrument against the shrinking amount of power actually available to run it. At some point within the coming years, the spacecraft's power output will finally fall below the minimum threshold needed to operate any remaining instrument at all, and Voyager 1 will go permanently silent, carrying with it whatever questions about interstellar space still remain unanswered at that exact moment. Which means the persistent plasma signal Voyager 1, first detected back in 2017, isn't simply a fascinating historical discovery. It's an active, ongoing measurement, still genuinely valuable, still actively being studied, coming from what remains, even now, the only functioning scientific instrument humanity has ever placed directly inside interstellar space. Every additional year, Voyager 1 continues operating adds more data to a real-time record of an environment that, once this spacecraft finally falls silent, nobody currently has any concrete plan or funded mission capable of directly measuring again for at least another generation. So, is there a mysterious signal coming from Voyager 1, connected somehow to the edge of our solar system that scientists have spent years trying to fully understand? Genuinely, yes. And that's precisely what makes the real version of this story worth telling properly, rather than dressing it up with language it never actually needed. Not a transmission from something external reaching out to us, but something considerably rarer and, in its own way, more remarkable. The actual physical sound of interstellar space itself, picked up directly by a single aging instrument still faithfully doing its job, nearly 50 years after it first left Earth, revealing that the vast, quiet-seeming darkness between the stars is nowhere near as empty or as silent as anyone ever expected it to be. If stories like this, The ones where the real, patiently gathered scientific signal turns out to be more genuinely fascinating than any invented version of it, are what you come here for. Stay close, because Voyager 1 is still out there, still listening, for however many years it has left.